All right, hello, greetings, welcome. In this screencast, we're going to take a look at our homework problem for Chapter 9. So flipping over to Chapter 9, right, here is our problem statement. So it's an isothermal batch reactor with a simple reaction of A goes to B. So the conversion of A to B takes place in an aqueous solution in an isothermal batch reactor. The reactor is charged with 1,200 liters of a 2 molar solution of A at 300 Kelvin. Recall 1 molar is 1 mole per liter. Calculate the time required to reach 0.8 fractional conversion of A. The fractional conversion of A may be computed as this, where Na naught's the initial number of moles of A at T equals 0, and Na is the number of moles at a given time. The reaction is first order in A, and the rate coefficient obeys the Arrhenius expression with the pre-exponential term equal to this. And here's my activation energy, right? So we're given all of this, and there aren't as many details, okay? But remember, part of that is the last section, right? So the last section of the text works out the design equations for the case of an isothermal batch reactor. All right, so our main equation that we're going to be working with, right, is going to be, we'll write our differential equation with respect to Ca, right, because we'll take V, the volume, to be constant. And so it's going to be dCA dt is going to be equal to, in this case, negative kCa, since that section, right, is also just for the simple reaction of A goes to B. Okay. Cool. So I'm going to go ahead and I'm going to jump over to MATLAB and let's solve this. Okay. So just like in class, I'm going to take this in pieces. So I'm going to start by, I'm trying to solve a differential equation. So if I'm trying to solve a first order ordinary differential equation with MATLAB, I'm going to start by writing a rate function. So I'm going to write my rate function. I'm going to solve, generate a plot, and make sure things are working correctly, and then I'll build up my code from there. Okay. All right. So I'm going to start with function res, and I'll call this rate fun. Okay. My rate function needs to have two input variables. First is going to be time t, my independent variable, followed by my dependent variable, which in this case, let's see, I have a differential equation for, I could write just a single differential equation, and I guess I'll do that in the context of Chapter 9. We haven't talked about systems yet, but I'll just write down my differential equation for A. Okay, so in the next chapter we'll have systems, right? And so we could write our differential equation for both A and B, or my non-steady state mole balance for A and B. Okay. All right, so I have my rate function. It's going to have an input of T and Ca. Okay, I'm going to come over here now, and I'm going to start by gathering up some of my constants. And so first I have my K naught. So it's my pre-exponential term. Okay, so K naught is going to be equal to 2.4 e to the negative 2.4 e to the negative 8, and that's in units of inverse seconds. My activation energy is 15.3 kcals per mole. Okay, and so that's E, and kcals per mole is 15.3. Okay. Now remember, I only remember R, my molar gas constant, in joules per mole Kelvin, 8.314. And so I can either take my activation energy and convert that to joules, or I could take my molar gas constant and convert the joules there to kcals. Okay. I'm going to go the route of converting this to joules. Okay, and so this one is in kcals per mole. Okay, and in part only because I have also burned in my head the conversion factor from joules to calories. I believe it was from general chemistry. So E and so joules per mole. So I'm going to take my energy in kcals per mole, and first I'm going to multiply by 1,000. So now this is calories per mole, and then I remember 1 calorie is 4.184 joules. So 1 calorie is 4.184 joules. All right, so if 1 calorie is 4.184 joules, then I'm going to multiply by 4.184. because that's joules per calorie. Okay, so now this should be in joules per mole. Okay, great. Need my molar gas constant. Okay, and so that is R, and now I only know 8.314. Okay, and so that's joules per mole K. Temperature, and so we have, oh, actually I should look, what was the temperature? Temperature is 300 Kelvin. Okay, and that should be enough to calculate K. So let me say now computing my rate constant. Okay, so K is going to be equal to K naught times the exponential of negative activation energy divided by RT. And remember, it's the product of RT, so I need that in parentheses, so R times TK. Okay, so there's my rate constant. Cool. And now that I have my rate constant K, remember my differential equation then? Okay, my differential equation is going to be dCA dt, right, is equal to negative K times CA. Okay, so now computing all right, now I'll comment, right? So normally I would make this res, okay? If it makes more sense to you too, all right, you could also say, okay, this is dCA dt, right? You could call your variable something like this. Normally I would use res, but you could also do something like dCA dt, right? If that makes more sense to you and looks like your differential equation. So my rate expression is dCA dt is equal to negative K times CA. Okay. MATLAB is going to, oh, actually I forgot a couple of things. So first I'm going to say MATLAB's going to complain because I have this input variable of t. But remember, MATLAB expects a rate function with two input variables. So what it's actually suggesting is that since t is an input, it's not used. Okay, remember you could put tilde in there as a placeholder. Okay, I have a tendency to put t in there just because then my rate expressions always look the same, and then I have burned in my head that this is what the format or general format of my rate expression must be like. Okay, here E in kcals, right, is underlined. Okay, why? That means it's not actually used. And when I look at the next line, it's because I just manually typed in 15.3. Okay, so I'm going to make that E in kcals just to make it more clear exactly what I have and to generalize it. So there's my rate expression. Within the problem statement, so I'll save it as rate fun. Within the problem statement, they also gave us initial concentration and things like that. But that is used when we solve, not here. Okay. And I should note, E is in joules per mole Kelvin, R times T, right? That's going to be, my activation energy is in joules per mole. R times T is going to be in joules per mole. So my exponential term is dimensionless as it should be. So K is in units of inverse seconds, right? The same as K naught. Okay. All right. So now coming back, okay, I have my rate function, okay, and remember my rate function is, the first step is I'm going to take my expression and I'm going to write it in the form so that I have the derivative of my dependent variable with respect to my independent variable on the left-hand side. Okay, so I have this, and let's check to see if it works, right? So I'm just going to run it, make sure it works, and then I'll build up my code. And so we're told that the reactor is charged with 1,200 liters of a 2 molar solution, right? And so what this is going at is, for this problem, I could solve in terms of concentration or moles. Okay, I'm going to solve in terms of concentration. And so I'm going to use as my initial condition, Ca naught, right, is going to be 2 molars. So initially I have 2 molars. So I'm assuming volume's constant. It's discussed in the previous section. And so I could just as well, instead of using moles here, use concentrations as well for my fractional conversions. Yeah. Okay. So coming over then, and actually let me make one more kind of comment about my rate expression. So we said K has units of inverse seconds. Okay, so concentration is going to have units of a molar. So moles per liter. So the right hand side of my equation, right, has units of molar, right, per second. Okay, so molar per second, right, which makes sense. This is dCA dt, right, has units of molar per second. And why I say that is, okay, that's molar per second. So when I integrate that, my unit of time is going to be seconds. So when I start integrating, I'm going to start integrating at t equals 0. But then that unit of time, when I specify a range of times that I'm integrating over, that's going to be in terms of seconds. Okay. So I'll get concentration in molar versus time in seconds. Okay. But all right, so all I'm going to do first is I'm just going to solve this in the command window and make sure it works. Okay, and so initial concentration again was 2. Okay, so I'm jumping over to MATLAB, and to solve, I'm just going to type ODE 45 at rate fun. Okay, we're going to start integrating from a time of 0, and I'll just give it some big number, 1000. Initial concentration is 2. So if I call it without any outputs, right, it's going to make a plot. Oh man, looks like it's just stuck at 2. That doesn't look too cool. Okay, let me put another 0 and see if it still doesn't change. Okay, still not changing. Okay, so I've got something wrong here. So my rate function, so there's K naught, right? Let me double check. That's 2.4 times, 2.4 times 10 to the 8, not negative 8. Okay, so 2.4 times 10 to the 8. Let's see if that fixes it. Yeah, and now I have this exponential decay function like I'd expect. Right, perfect. So again, I ran in the command window, I was doing it to make sure I didn't have anything that was broken. But there I was able to catch the typo in that my concentration wasn't actually changing. All right, so now we've got that. And remember, Professor Pluch likes to use functions with no inputs, right, and kind of in place of scripts in terms of packaging things up. So you could just as well use a script, but I'm going to create a new top function. Okay, I'm going to call this, maybe I'll call it batch fun, right? Okay, so I'm going to create a new function, top function. Res is, I'll call it batch fun. It's going to have no inputs. I guess initially you could even make it so it doesn't have any outputs. Okay, and I'm just going to start by solving. Well, actually, let me define my parameters. So my initial concentration, which I used, that was Ca naught is 2, and that's in molar. Okay. My initial time, all right, T naught was equal to 0. And I'm going to say that's in seconds. And then my final time, I'm going to call it T final. And I'll just make that a big number. Looks like I had 10,000 there. And that is going to be in seconds as well. So then solving. Okay, I guess it's okay if I cover up my rate function since you've seen it already. But then solving, if I want to instead store the output to variables, right, I'll have a call like this. Come on, MATLAB, I don't want you auto-correcting things. Boop. And so it's going to be ODE 45 at rate fun. Okay. Now this is going to be integrated from T naught to T final. Initial condition Ca naught. And I'm going to plot. So I'm going to open up figure 1. And I'm going to plot T is my x variable versus Ca is a black line. Cool. X label is going to be time in seconds. Y label will be the concentration of A, and that's going to be in molar. Cool. So this is just saying, hey, you're not outputting anything, and that's fine for now. Okay, but if I run it, now I have a plot, looks just like my other one, concentration of A in molar times time T in seconds. Okay, great. Okay, now I'm gonna make some tweaks. Okay, so what I'm gonna do in terms of tweaks is, well, that's time in seconds. That's great, or not time in seconds. That's my concentration, but it asks for things in terms of my fractional conversion, right? And so what I'm looking for is, so Na naught minus Na. So all the moles of A that enter my reactor, okay, and then this is the moles coming out. Okay, so this is moles going in, moles coming out. So the difference is the moles that have been consumed in the reactor. So we're looking at the moles of A consumed relative to the initial number of moles. And so it's what fraction of my moles of A, my reactant, have been consumed. Okay. And, so some of this is going to be extra, but it's good practice. So let me do computing fractional conversion. So FA, let me just do FA, is going to be equal to CA naught minus CA. Put that in parentheses. Element-wise operation divided by CA naught, right, since CA is a vector. And then let me add another figure. Okay, and I'm going to plot in figure 2 fractional conversion of A versus time. Okay, and that's dimensionless. Okay, cool. So I just calculated fractional conversion. I'm going to plot that in a second figure window. So figure window 1 and figure window 2. Okay, it looks like it goes through a fractional conversion of 0.8 somewhere around here. Looks like around 940 seconds. Okay, and then what happens is eventually it's going to reach a fractional conversion of 100% or fractional conversion of 1. Right, all the A has been consumed, and it'll just be constant and equal to that value. Right, just like here, my concentration goes to 0. All right, so the first thing is, even here, I could keep this in terms of seconds. You could also convert your time to minutes. And let me just do that just so you can see, because the key is you're not going to convert your time to minutes within your differential equation, right? In general, I wouldn't mess with that, right? I have K in terms of inverse seconds, so you could convert it to inverse minutes, but that's just asking for me to make an error of having an inverse somewhere. So instead, what I would do is, if I wanted minutes, okay, when I solve, okay, this is my constant. I'm going to get a vector of my concentrations and the corresponding time t. And so you're just matching up the elements in that vector. If you wanted time in minutes, what I would do is I would just take this vector here, and I'd say t min is just going to be equal to t divided by 60. Okay, and actually a period divided by 60. Right, and so this would be time in minutes. And then when I plot, I would just plot t min, update this to min, and do the same thing here. All right, so if I wanted a different unit of time, right, I would more than likely solve in terms of seconds, so that way I'm not actually messing with the conversion, and only because it's inverse second, which is more likely for me to make a mistake in terms of converting. Compute the time as normal in seconds and then convert. And here as it is in seconds, so now it looks like it happens somewhere around, or minutes, looks like it happens somewhere around 15 minutes. You could also convert to hours, right, and that would look exactly the same. Okay. All right, but let me try and look at what the problem asks for. All right, so I solved it. We've got some nice plots. We're asked to calculate the time required to reach a fractional conversion of 0.8. Okay, cool. The time it takes to reach a fractional conversion of 0.8. Cool. All right, so I have kind of a lot of stuff here. Okay, and that's okay. So again, I'm going to maximize this. What do we want to do? So if I am trying to determine when I have a fractional conversion of 0.8, let me kind of take this in steps. And actually, I'm going to leave all of this because I like the plots, right? And so this is, I'm going to say this is solving over a wide range in plotting, right? So I'm gonna keep this part, even though this, okay, is, I'm gonna put a big line on here, right? This is, kind of optional. And actually, solving over a wide range in plotting, okay, I'm actually going to put that here, okay, and I'm going to say that of, this is kind of optional, wasn't really necessary, but it was a good exercise as we work to master MATLAB. All right, so as I build it up though, of, first what I want to do is I'm going to take a step and I want to try and create the equivalent of a, I want to try and create the equivalent of an analytic expression, right? So if I were solving this analytically, what I would obtain, or what I'd solve for, is a function of the concentration as a function of t. Okay. When I solve it numerically, as I do here in MATLAB, what do I get? Is I get a vector of concentrations and the corresponding time. And when we looked at those in class, remember the only values I know exactly are the first element, so T1 and C1. That's the first element of T is just T equals 0, my initial time. The final element of my T vector, so T end, is T final. So those are the only two values that I know are going to appear exactly in my output vector. In terms of all the other ones, remember, you can just think in your mind that MATLAB is choosing delta t on the fly to achieve a given level of accuracy. And so if I want to create something that looks like a function, I'm going to do it via an anonymous function, right? So what that might look like is I'm going, well, no, I'm not going to do it as an anonymous function. I'm not going to do it as an anonymous function no. Yeah, I'm not going to do it as an anonymous function, because my anonymous function, I'm just going to have that single output. Okay. And so how we create it, okay, is I'm going to create a new function. So this could be function res is, oh boy, now I got to think about, sorry, I'm having a, no, I'm getting tripped up because I have all of this extra stuff, which is me solving over a wide range. Okay, so I take it back. I'm going to comment this out for now, and then we'll come back to this, okay? All right, so how I get the equivalence of an analytic function, right? And I'm going to come back to this. And so I'm going to start by, I'm going to have this my batch function, and I'm going to give it an input of t, right? So what I'm trying to go for here is I want to create a function where if I pass t to it, it'll return back the concentration or fractional conversion at that time t. Okay, and I'm going to make a note here that my input is time in seconds for now. Okay, so what I'm going to do in this case is I'm going to solve. Okay, but when I solve, okay, I'm going to solve over the range of t naught to t. So instead of t final, I'm going to put in t. So the user is going to specify a value of t at which point they want the concentration. And so then I'm going to solve over the range of t naught to t. Okay. Why? Because again, when I look at my output variables, the first element, right, of CA is going to correspond to the initial concentration. The last element is going to correspond to the concentration at my final time, which is at t, which is what the user is looking for. Okay. So in that case, res will just be equal to, res is going to be equal to CA end. And actually, okay, I could uncomment this out now. Well, actually, yeah, let me uncomment this, right? And so what I could do is then I could add this to my plot. So maybe let me open up back figure 1, have a hold on, okay, and let me just plot the data point on that graph just so we can see what we have. And so I'm going to have point T, and then I call it res here. It's CA, and actually that's big CA end. I'm going to plot that as a black circle. Okay. So now what my code would look like is that I just can't click the run button. Okay, but if I call it, and let's say I want to know the concentration at a time of 500 seconds. Okay, and actually my figure is messed up. All right, why is my figure messed up? Because my latest version, we converted the time to minutes when we plotted. Okay. So one way would be just to take t here and multiply by 60 to get it in minutes. Okay. Boy, now I'm all sorts of messed up. Okay, so that divide by 60, Dr. Paluch. Divide by 60. All right, now we got it. All right, so now here's my plot of concentration. Okay, and there, if I specify a time of 60 seconds, all right, we see where it falls on my line, right? And then we just continue to integrate more. And here's my plot of fractional conversion. Okay, and maybe, okay, what we really want, let me put this as CA end. Okay, maybe what I really want is to return the fractional conversion. Okay, and that's going to be CA naught minus CA end, right? I just want that fractional conversion at that time t divided by CA naught. Okay. And then I can actually add that to figure 2. Hold on, and I'll plot t divided by 60 versus res, and I'll also plot that as a black circle. Okay. So now when I run, okay, my code's actually returning the fractional conversion now of A. Okay. Concentration, man, I broke it. Let's fix it. So fractional conversion falls on there. So the issue is then when I solve down here, right, I have CA again. Okay, so this is, so if I want to reuse this, so I'm going to call this like CAF maybe, I don't know. Maybe this is my final or the actual answer I'm looking for. Okay, so the issue is then I overwrote CA here. Alright, so fractional conversion, beautiful. Concentration, beautiful. So I see my point right on that graph, and then it returns the fractional conversion. Alright, so now I have some function, whereas the user specifies, when the user passes a value of t, it returns back the fractional conversion. Great. So what I'd really like to do though is, the problem says, is I want to be able to solve for the time it takes to achieve a specific fractional conversion. And so what am I going to do? Okay, so I'm going to save another copy of this, and this is going to be like batch fun, maybe like t. Okay. And so now in this batch fun t, I'm definitely going to want to come out all these plots. Okay, because if I use fzero and I keep calling this function repetitively, it's going to generate a ton of plots. Okay, so batch fun t. Okay, it's going to be just like the last function I just had. I called the wrong one. Batch fun t. Okay, it's going to work just like the other function I just ran, but no plots. Okay. All right, so now I have some function that I pass t to it. It returns back the concentration at that given t, or it returns back the fractional conversion at that time t. Actually, I'm going to keep this as batch fun. Okay, and I'm going to create a new function. It's called batch fun t. Okay, and batch fun t, the input's going to be the fractional conversion I'm solving for. And so this will be the fractional conversion we want to find the t for. Okay. All right. So I have batch fun, where if I pass to it a value of t, it's going to return the fractional conversion at that t. So I'm going to solve for that corresponding t using fzero. Okay. So just like we did in class. Now, fzero requires an error function so that when I find the value of t, my error function returns a value of 0. How I'm going to achieve that is I'm just going to create an anonymous function. And so my error function, okay, is going to have as an input of what am I trying to solve for? T. Okay. When I pass that value of t to my error function, what do I want to call? I want to call batch fun t. Okay. But then what I want to do is I want to subtract. So batch fun t will return the fractional conversion at that time t. I want to subtract from it the value of the fractional conversion that I'm trying to solve for. So this is going to return back the value of my fractional conversion at time t, and I'm going to subtract from that the fractional conversion that I'm solving for. Okay, and so then in terms of solving, okay, so then my solution, solving for t in seconds, okay, so solving for t in seconds, it's going to be fzero error fun. Okay, now my search range. So we looked when we plotted from 0 to 10,000. By the time we hit 10,000, we had a fractional conversion of 1. Okay, great. So it would be tempting to just search from, say, 0 to 10,000. And actually for, kind of these exponential decay and growth models, for this exponential decay model, right, it's eventually the concentration is just going to hit 0, right, and it's just going to stay at 0. A fractional conversion is just going to go to 1. So you could go to some huge value, all right, and it should still work, all right, it's going to take longer to shrink that range down. Okay. But my lower bound can't be 0. Okay. We can't have a lower bound of 0, and the reason being is what fzero is going to do is, and it's the first thing it's going to do is it's going to try and evaluate my function at those two endpoints, which would ultimately lead to calling this function at those two values, and would correspond to solving my differential equation over a range from 0 to that value of t. And so 10,000 is fine, right? That worked before. But I can't, if you give it a value of 0 and it tries to integrate from 0 to 0, you're going to get an error because you can't create a vector that goes from 0 to 0. Right? So it's going to be an empty vector, so it's not going to actually do anything. So instead of 0, just want to make this a tiny value. I'm going to use, say, 1e to the 6. Okay. All right, so now if I save this, so now my code works that if I'm looking for a fractional conversion of 0.8, okay, it returns a corresponding time in seconds. Now let's say I wanted the time in minutes, right? So maybe that's TS. If I wanted it in minutes, all right, I could do that. All right, I could do, say, res is t in seconds divided by 60. All right, where t is in minutes. So now I've got some code that if I specify a fractional conversion of 0.8, it gives me the time it takes to get that fractional conversion in minutes. Okay, great. Great. And if I wanted to throw this in the plot, okay, I could do that in a couple different ways. Okay, so this is batch fun. Okay, let me just copy this, and I'm going to create. And this isn't going to be the most efficient code, but let me call this like batch fun plot. Okay, it has no inputs, and what I'm going to do is I'm going to get rid of this, and then I will uncomment out our plot business, and I'm not gonna. Okay, so I'm gonna create this batch fun plot that has no inputs and no outputs. All right, so I could even get rid of the output, and MATLAB will be happier with that. It's just going to solve my diffie q over some big range, and it's going to plot it. Okay, so then batch fun t. Okay, I don't actually need this. Okay, since I just put all the plot part in a different function. Okay. And then I can just say, hey, plotting. And so I can start by calling batch fun plot. Okay, and then within figure 2, okay, I could add my point and make sure, use it to check my solution. So within figure 2, I will hold on and I'll plot. So res is my time in minutes versus versus FA, the fractional conversion that was inputted. And let me do that as a say red star this time, so it really pops. So now when I run, okay, it gets me my value. And look, here's figure 1, concentration is a function of time. Hey, there's my plot with fractional conversion. It falls on the line. Okay, and you know, if I wanted to, let me shrink this up a little bit. All right, and I could just as well do everything in terms of minutes and switch to seconds. Okay, but if I change that to 360 seconds to plot over, well then it doesn't like me. So what did I do? Oh, 3,600. Okay, there we go. So figure 2. Right, there's my fractional conversion as a function of time in t minutes. Right, by the time you get to 60, it has like a fractional conversion of 1. All right, here's my concentration decreasing. We get pretty close to 0 by the time you get to 60. Okay. So, you know, that's kind of unnecessary, but it was nice to check my results. And, you know, if you wanted me to, I could keep talking and I could keep building this up and playing with it. Okay, but it's kind of fun. And hopefully once, you know, things start to make sense to you, you can have fun like this too. And so I guess just one last note again here. Okay, they're saying, hey, you don't actually use t. So what they would prefer is if you put a tilde in there, right? Tilde serves as a placeholder. And my rate function, right? They'd prefer if you just put a tilde in there as a placeholder. Okay, I have a tendency to not to, just so I remember, right? My rate functions all look exactly the same. Right, the output from ODE45, right? It's always going to look exactly the same. Okay, but if I put those two tildes in, right, I still get the exact same result. Right? It doesn't make a difference at all. But yeah, and just think you can make additional input variables to this. They could be maybe this plot range, right? So maybe I put like t range in here, and then maybe batch fun plot has an input of t range. Okay, which is instead of t final. Actually, I can call it like t final here, and then I don't even have to update anything. Okay, so now when I call it, I can give it 10,000, right? And we have our initial plot. I could give it 3,600, right? And I have that plot we just had, right? So, you know, there's a lot you could do to really make this nice code and make it your own. Okay, hope that helps. If you have any questions, by all means, let me know.